This is Note Taking Guide 7.6 for mathematical decision making for life. Today we're going to talk about Euler's formula again and something called a minimum spanning tree. So the first thing that we need to talk about is the definition for what a planar or planar graph is. A graph that can be drawn on a plane in a way that its edges intersect only at their endpoints or vertices. In other words, it can be drawn in such a way that no edges cross each other. All planar graphs divide the plane they are drawn into a number of areas called faces. When counting the faces, remember the plane they are drawn in would be counted as one area. So let's talk about what that means here for just a minute. So faces are the flat surfaces formed. So we have this triangle flat surface here. Here's a second triangle flat surface, a third triangle flat surface, 4, 5. But we actually have 6 faces because we have the plane that figure is drawn in, the flat surface that figure is drawn in. How many vertices does it have? 1, 2, 3, 4, 5, 6. So 6 vertices. And then how many edges does it have? I like to just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 edges. Now it's not necessary to kind of junk it up like that. If you kind of want to, you could even do it with different colors. So faces, I have 1, 2, 3, 4, 5, 6, 7, 8, counting the plane that it's drawn in. Vertices, I have 1, 2, 3, 4, 5, 6, 7, 8 on the vertices, and then edges. Sometimes I like to just use a marker and trace them so I don't get confused which ones I've done. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 different edges. So that's how we count those, okay? Again, faces here, flat surfaces. So we're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 on the faces. Oh, I'm sorry, plus out here, 14. That's the hard one to not forget, is that one that is not closed in. So 14 faces. Vertices, we're just going to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices. And then edges, like I said, I always like to kind of highlight them. I think it makes them easier to be seen when we're highlighting them so we know which ones we counted. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 different edges. Now you guys, just a minute ago when I was like, 13 right here, and then I was like, oh, I made a mistake because I forgot that one. One of the reasons I knew that is because I have done this problem before, so I kind of just knew that. But another reason that I would have known that I was making a mistake is there's actually a pattern in how we get from the vertices and faces to the edges. So take a look at this for just a minute. Vertices and faces add up to 12. Edges is 10. So 12, how do I get to 10? I subtract 2. Vertices and faces add up to 16. The edges are 14. So add them together, subtract 2. Here we do it again, add them together, subtract 2. So we have a formula that Euler came up with that says vertices plus faces equals edges plus 2. So V is for vertices, F stands for faces, E stands for edges, and then we just add 2. So if we have that formula and we know that our graph is going to follow that formula, then we don't even have to count. So on this example though, vertices, we have 1, 2, 3, 4, 5, 6, so 6 vertices. On the edges, I'm gonna highlight them. So 1, 2, 3, 4, 5, 6, 7, 8. I think I got all of the edges that time, so 8. So if the graph is planar, what must be the number of faces? So we know vertices, which is 6, plus faces equals edges plus 2. So 6 plus a number has to equal 10. The number is going to have to be 4, so the number of faces is going to be 4. So now we need to redraw the graph so it only has 4 faces. You guys, when you look at this, this is not planar. It intersects inside a lot. So a planar graph is one that doesn't intersect anywhere except for the vertices. So if you look up here, none of the lines intersected each other, just in the vertices. You guys, this takes a lot of guessing and checking to do this. I've previously done this already, so I know what I can do to make mine look appropriate. But I'm just going to write down all of my vertex points. So I have A, B, and C. I'm going to throw E inside right here this time, and then I'm going to put D down over here. So when I look at B, B has to go to A and to D. So B goes to A and B goes to D. Okay. When I look at C, it has to go to A, to F, and to E. So C has to go to A. Oh, I didn't put my F on there yet. I'm going to put F up over here. C goes to A, to F, A to F, and to E. Okay, now I'm going to go around to D. D has to go to B, A, and F. So D goes to B, to A, and to F. E goes to C and to A. So E goes to C and to A. Still no intersection, so I'm doing great. F goes to D to C. So F goes to D and to C. It already does. And A goes to E, D, B. So E, D, and B. And so E, D, B, and C. And it does go there too. So here's my graph. How many planes do I have? Or faces do I have? Because I know I have to have 4. So I have 1, 2, 3. And then you guys don't forget 4 is outside in that plane. So I actually have the 4 faces that I need, and I drew that planar. So planar just means redraw the graph so you don't have all of these intersections inside the graph. Okay, doing it again, trying to draw this one. So how many vertices does this have? 1, 2, 3, 4, 5, 6. How many edges does it have? Again, I think it's easiest to highlight so we don't get confused. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges is what I counted there. And then it says, well, how many faces should they be? Now, if you remember, vertices plus faces equals edge plus 2. So vertices plus faces equals edges plus 2. So the faces added with 6 has to equal to 14. So the faces are going to be 8 because 6 plus 8 equals 14. So I have to draw this so that it has 8 faces and so that it's planar, meaning that it doesn't repeat anywhere or cross over inside. So you guys, this one was really complicated. It took me 2 or 3 times before I got anywhere close to this. So I'm just going to draw the one out that I came up with. You guys can try it and see if you can get a different one. There's clearly could be more than one answer on these if you're working hard at trying to find one. But this is how I set mine out. So I knew A had to go to B, C, E, and D. So A goes to B, C, E, and D. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, B goes to A, D, E, F, and C. So to pretty much everything. A. Now the only way I can get it to D without going through is to go around. So A, D, The same thing with E. I gotta go around to get to E. So around to get to E. And then C and F. So it goes to C. And it also has to go to F. So I just went around like this. Okay. C goes to B, A, D, and F. So C, B, A. I'm going to go, C goes to E and F. And E has to go to D too. So it comes down like that. And then I just keep going around until I get every piece to every piece that it needs to be. And I just double check. So F has 3 coming in, 1, 2, 3. E has 1, 2, 3, 4, 5 coming in, 1, 2, 3, 4, 5 coming in. D has 3, 1, 2, 3. A has 1, 2, 3, 4, 1, 2, 3, 4. So I can tell that I did it right. You guys, none of my lines intersect each other, so I did it right. So if I did do it right, though, how many faces should I have? I should have 8. So I have 1, 2, 3, 4, 5, 6, 7, and then outside in the plane is 8. So you just kind of have to mess around with it until you get the right number of faces they're drawn. Like I said, that took me 2 or 3 times before I found that that would work if I did it that way. So sometimes drawing the planar graph is harder than you think it's going to be. All right. If a connected graph has 4 vertices and 6 edges, how many faces must it have? So again, vertices plus faces equals edges plus 2. So 4 vertices plus however many faces equals 6 plus 2. I know my faces have to be 4. Then it asks if I can draw the example of that. You guys, I only have 4 vertices. So 1, 2, 3, 4. So 1, 2, 3, 4, 5. If I go this way, I cross, and I can't do that. So I can't have my points set up like that. So I tried a lot of different ways, and I came up with this one that looks like this, kind of like the Y. So I went 1, 2, 3, 4, 5, 6. And then I counted my faces to make sure I had them. I had 1, 2, 3, 4, which was the right number of faces, which means this will work as a planar graph as my solution. So like I said, you guys, it's really about guessing and checking. There's not a way to figure this out without just figuring it out. Okay, next problem. If a connected graph has 9 faces and 13 vertices, how many edges must it have? So again, vertices plus faces equals edges plus 2. So we have 9 faces and 13 vertices. So this equals 22. So the edges have to be 20. Okay, so we have 9 faces, 13 vertices. Again, you guys, I tried this several times on an extra piece of paper before I found out the correct method. So you might have to try a few times on your homework, but this is the one that I ended up with. I went like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 vertices, and then I started connecting them. And then I counted to see if I was right. So I need to have 20 edges. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I got them, you guys. That's what it's got to look like. Now, there may be other ways to do that. That's just one that I found that worked. Again, it took me 2 or 3 problems before I figured that out. Okay, next problem. Now, the trees are easier in my opinion. A connection of a network has no cycles or circuits, no loops, no multiple edges, then it's a tree. Here's examples of trees. They start and they go to every vertice, but not necessarily in any particular order. Because there's no circuits in these networks, they take on the appearance of trees. So here's an example, spanning trees. Every connected graph will have at least one subgraph that is a tree. If the tree is a subgraph, connects all of the vertices, then we call it a spanning tree. Here's my original graph. You guys, all I have to do is get every vertice to every vertice. Do you see how A goes to F in this one, then to C, out to D, down and back? That's a spanning tree for these. So all I have to do is get to every vertex point, drawing a tree. Okay, so we can do the same on weighted graphs. So here's an example of 11 different spanning trees for this graph with their weights. If we can do that, then we could more easily figure out the weighted graphs and how much faster or how much time we can save doing different kinds of graphs on our maps. Okay, so that's a lot of figuring out spanning trees though, so maybe we need to see if there's a rule for this. So what they did on all of those spanning trees was they found their weight, and they're like, oh, here's the least amount of weight here, 14. So that would be my minimum spanning tree, the best way to get from point A to point B. So how are we going to do that? It would be impractical to list out this many chances on every possible spanning tree. So what we're going to do is we're going to use a rule that's called Prim's algorithm. Prim's algorithm says this: choose a starting node, anyone will work. From that node, choose the edge with the least weight. Now you have two vertices that are connected. Look at the remaining edges connected to either of those vertices and choose the one with the most weight, and then you just keep continuing with that theory until you've used all the vertices. So let me show you what I'm talking about here. Let's just choose a vertex. Say I choose vertex B to start with. I look at vertex B and I'm like, oh, I could go 6 this direction, 3 this direction, or 10 that direction. Well, the least amount of number is 3, so I'm going to go to 3 and use vertex F. Now looking from B, I'm like, oh, I have 6 this direction or I have 10 that direction, but I can also look from F now. I have 1 this direction or 7 that direction. Well, 1 is the least amount of numbers that I can gain, so I'm going to go from 1. Now I can't go here because that closes me in on my shape, and I can't close my shape or it's not a tree. So from there I can either go this direction with 7 or I can go this direction with 10. Well, 7 is the least amount of numbers, so I'm going to go with the 7. Then when I get over here, I can't go this way because it closes my shape, so my choice is 9 or 6. Well, 6 is the smallest number, so I'm going this direction. And then my last choice would be to come over here this direction to E. So there's my minimum spanning tree because I started at a point and I chose the least valuable way to go until I found my tree. So what's the value of this tree? It would be 1 plus 3 plus 7 plus 6 plus 5. And I can find the value of that tree. The value of that tree is 22. And the way I could list that tree is by the letters that are involved in that tree. Okay, so that's how we do minimum spanning trees. Hopefully that was enough to help figure out how to do your homework. If you're having questions or problems, come and see me. Let me know. Good luck with your homework.